Hey, welcome back. This is Prof. Scangrella. This time we're going to look at series and parallel circuits. Again, we're looking at series and parallel circuits, combination circuits. So there's a couple things that we need to do when we want to resolve or solve series parallel circuits, right? Now, of course, before we start, I'll just give a quick review of parallel circuits and a quick review of series circuits. Let's start with the parallel, right? So again, here I'll just draw a quick circuit with two parallel loads. So this is a parallel circuit right here. And the points that we made about the parallel circuit, we said that the voltage across the resistors is the same, right? So the voltage is the same. And we also said that we can calculate the load for each resistor, right? So the current going in the resistor is based only on Ohm's law. So each resistor will draw its own amount of current. So if you add another load here, it's going to draw its own amount of current based on Ohm's law. So we said the voltage is the same, and we said each load will draw its own current. So each load will draw its own current. And we also said that we use the principle of Kirchhoff's current law that says that the current entering the node is equal to the current leaving the node, right? So if this is our total current here, it's going to equal to I1 plus I2 plus I3, right? This is called Kirchhoff's current law, KCL, and it says that IT is equal to I1 plus I2 plus I3, right? This is Kirchhoff's current law. Okay, the next thing we said about the parallel circuit was that the resistance, so the power in the parallel circuit, the power is going to be equal to the power of all the loads. So it's going to be the power in R1 plus the power of R2 plus the power of R3, right? Plus whatever. All right, then we said the resistance in a parallel circuit, we cannot calculate the resistance straightforward. Of course, we can use Ohm's law. We can say that R is going to be equal to the Vs over the total current, right? We can find the resistance this way, or we can use the reciprocal method, which is going to be R is equal to 1 over the sum of the conductances, where we have 1 over R1 plus 1 over R2 plus 1 over R3, right? So then we also said we can find the parallel resistance by using the product over the sum. So for two resistors, it will be R, let's say R1 times R2. So let's say that R12 is equal to R1 times R2 over R1 plus R2, right? So this is how we find the resistance for two parallel resistors. So this was for parallel resistors. Now let's take a look at series circuit very quickly. A quick review of series. We'll start with a battery. And we have two series resistors here. All right, so again, we are saying that the first thing we said about the series circuit, this is the series. Put the P here for parallel. We said that the total resistance is going to be the sum of the resistances. And then the next thing we want to find is the current is going to be the voltage over the total resistance. Then we also said the way we find the voltage drops, we can use Ohm's law or we can use the voltage divider method. So here we have KVL, and that tells us that our voltage source is equal to the sum of the voltage drops. Right? Now, again, we are saying that we start with a particular voltage here, we drop some across this resistor and the rest is across here. So if you took your meter and you're measuring right here, you're going to get the voltage across this second resistor right here. Now, this is called a voltage divider circuit. So to find VR1, we said we can use Ohm's law. So VR1 is going to be equal to the current times R1, right? Or we can use the voltage divider method, where we have R2 for VR2 over R1 plus R2, which is the same as RT. So R2 over RT times the Vs, and that will give us the voltage drop here as well. Now, in series parallel circuits, we actually now have combined of series and parallel components, that we need to observe, right? So what is an example of a series parallel circuit? Well, I'm going to give you a very simple example, right? And we'll do a couple examples here. So here's an example of a series parallel circuit, right? So the first thing that we need to do here, so I'll put SP, this is series parallel. The first thing we need to do for the series parallel circuit is that we need to identify the relationships, right, between the two resistors, right? So again, let's call this R1, R2, and R3. The first thing we need to do is identify relationships. And again, when we talk about relationships, we are saying identify which resistors are in series or which one are in parallel. Then what you will do then, you will replace the resistors with the equivalent resistance. Replace with equivalent resistance. All right? And then you're going to repeat. Step 3, repeat until you find RT. Right? So let's do it for this resistance right here, right? So what is the relationship between these two resistors? They're actually in parallel. And then if you replace these two with one resistor, that resistor will be in series with R1. So we can say that RT is going to be equal to R1 plus what? The parallel resistance. Now for this one, we can use the product over the sum. Let's say it's going to be equal to R2 in parallel with R3. And so if you were to ask, how do we find this? Again, how do we find R2 in parallel with R3? It's going to be R1 plus, again, the product over the sum, R2 times R3 over R2 plus R3, right? So again, this would give us our total resistance, RT. Now if we add some values here, like 1K and 2K here, and 1K here, we would have our RT being 1K plus 1K plus 1K times 2K over 3K. And again, a note of our parallel resistances, the parallel resistance is always smaller than the smallest resistor, so we expect a resistor smaller than 1K. So in here, our answer is 1K plus so that's going to be 1 over 3. Okay, sorry, it's 2 over 3, which is 0.66. That gives us 1.666K for our RT. All right. So again, step number 1, identify the relationship. What is parallel? What is series? And of course, for series resistors, you're going to add them together. For parallel ones, you're going to do the product of the sum. Let's do another example. We'll come back to this one here. All right. In this example, we have a rather complex circuit. Right, so this is our circuit right here. I'm going to draw it on this side. The circuit is here. So this is going to be our R1, 2.2K. This is R2, 2K. This is our 3, 47 ohms. This is our 4, 1K. This is our 5, 1K. Right? And you are told to find the following. Find RT, then find the total current, then find VR1, then find VR2, then find current in IA, and of course it's going to be the current here. Let's call this one IA. And let's find IB. And this current going down here, we'll call it IC. All right, and then let's find the total power. And let's find the power and resistor R3. All All right, so we're told to find all of these. Of course, we know the equations to find them. Let's find RT, all right? So again, to find RT, like we mentioned, the first thing you need to do is that you need to identify relationships, right? So we need to identify relationships. After we identify relationships, we need to get the equivalent relationship, the equivalent resistance. Find equivalent, and then we need to repeat this until we find the total resistance, right? So if we look at this here, we can clearly see that our resistance is going to be, our RT is going to be equal to, this one is in series, R1, plus, well, if you start in the back here, we have R4 and R5 are going to be in parallel. So R4 and R5, R4 is in parallel with R5. So let's put that in parentheses. Now this is going to be in series with R3. So we add R3 to it. All right, and then this is now going to be in parallel with R2. So all of this here is going to be in parallel with R2. And then the equivalent will be in series with R1. So to start this, we will start by finding R45, which is equal to R4 in parallel with R5, which is equal to, and again, for parallel resistance, we use the product over the sum. This is going to be equal to R4 times R5 over R4 plus R5. Okay, and that gives us 1K times 1K. Well, of course, it's going to give us half, so we have 500 ohms here. So 1K times 1K over 2K, which will give us 0.5K ohms, which is the same as 500 ohms, right? Then, so this is going to be replaced. We replace this one with R45 right here, right? Now, these two resistors, we replace them with 1, and now this is being seen as in series. So again, if you replace all of this here with one resistor here, right, we call that resistor R45. Now this resistor will be in series with R3. So if you want to find R345, R345 is going to be equal to R3 plus R45, which gives us 47 ohms plus 500, which is 547 ohms. All right. The next step is to find, so again, if you replace all of this here with one resistor, right? This resistor represents the value of our 345. This resistor now is in parallel with R2. You can see that it's in parallel with R2. And so now we can find R2, 345, which is equal to R2 in parallel with our 345, which is equal to R2 times R345 over R2 plus R345. And that gives us 2K plus 547 over 2K times 547. Again, 2K is 2000. And so for here we get the answer all right, hold on. So our answer should be less than 547. So the answer is 429.52 ohms, right? This is the answer we get for the parallel resistance. Now our RT. So again, if you replace all of this here with one resistor, we call it our 2, 3, 4, 5, 6. Then, right, the total resistance would just be these two resistors, right? So our T is going to be equal to R1 plus R2, 3, 4, 5, which is equal to 2.2K plus 429.52 ohms, which gives us 2.62952 K ohms. All right, so this is our answer. This is our total resistance. And now we can go ahead and find our total current using Ohm's law. The total current is going to be equal to IT will be equal to Vs over RT, which is, and again, I did not put the total voltage here, but the total voltage is going to be equal to 25 volts. This is 25 over 2629.52 ohms, and this gives us a current of 0.0097 amperes, which is the same as 9.7 milliamps. Right, so this is the current. This is the total current that is coming from our battery right here, right? Now, of course, we know that this current is going to be split up, and some is going to go down here, and some is going to go into IA, some is going to go into IB, and so forth. Whoops. All right, let's fix this. All right, so now we are ready to find, we have the total current, we have our resistance, we now are ready to find the voltage drop across R1. So we want to find VR1, and we're going to find that using Ohm's law. So VR1 is going to be equal to the current, which is going through R1, which is the total current, times R1, which gives us 9.7 milliamps times 2.2K, and that gives us a voltage of 21.34 volts, right? So this is the voltage that is dropped across this first resistor right here. Keep in mind that the total current is coming from the batteries, as it hasn't split up as yet. It's going to split up right here and right here. So this total current goes through this resistor, and we have a voltage of 21.34 volts being dropped across this resistor. So do we know the voltage that is left after this voltage drop? Yes, we know the voltage at this point right here. And this is the same voltage that is across R2, right? Because R2 goes to ground. This voltage that is left is going to be, according to KVL, is going to be 25 minus R1, and we're going to get our VR2. So we can find VR2 using Kirchhoff voltage law. VR2 is going to be equal to Vs minus VR1, which is 25 minus 21.34, and that gives us a voltage of 3.66 volts. Right, this is VR2. So now that we know VR2, so we know the voltage across this resistance right here, we then can find the current going through that resistor. Because again, if we know the voltage here, we know the resistance, we can find the current. So the current IA is going to be equal to VR2 over R2. Again, this is Ohm's law. So we have 3.66 volts over 2K, and that gives us 0.001926 amperes, which is the same as 1.926 milliamps. All right, so this is the current going through this resistor right here. Okay, Now, if we know the current going through here, we just found it, we can then know the current going there. So if we know the total current, which we know, and we know the current going in this branch right here, we can find the current that is left going in this branch right there. Because this current now is going to be split up into two, right? So this is, if this is IA and this is IB and IC, then this current here must be equal to IB plus IC, right? Because it's going to split up between them. So let's find this current. We'll call it IBC. So this current right here, we'll call it IBC. It's going to be IT minus IA. Again, this is Kirchhoff's current law. So we can say that IBC is equal to IT minus IA, which gives us 9.7 milliamps minus 1.926 milliamps, and that gives us a total of 7.774 milliamps, right? This is IBC, okay? Now, this is the current that is going through this resistor R3. And so if we know the current going through this resistor R3, and we know the resistance R3, we can find the voltage drop across R3. So we can find VR3 is going to be equal to R3 times IBC, which is equal to 47 times, let's fix that, 47 times 7.774 milliamps. All right. And that gives us a total voltage drop of 0.3. Okay, let me use my calculator. Maybe I'm making some mistakes here with some wrong values. Okay, 47 times 0.007774. All right, this gives me 0.365 volts. All right. Okay, so the next step after we found this this voltage drop here, right? So we know the voltage drop here is about 0.3 volts. So do we know the voltage after it? Because again, this voltage right here, which was the voltage across R2, is being split, right? Some is going to be dropped here and the rest will be across these two right here. So we can find the voltage across R4 and the voltage across R5. They're going to be the same by subtracting the voltage here from the voltage drop right there. Right, again, because we're going to go to 0 here, so the voltage will be dropped here and here. So now let's find this voltage drop here. So V, change color, VR4 is going to be equal to VR2 minus VR3, which gives us 3.66 volts minus 0.365 equals 3.295 volts. So this is the voltage that is left after that voltage drop. So this is the voltage across this resistor right here and the voltage across this resistor right there. And now we can determine the current that is going, that IB and IC. Now to find the current, we can choose to use the Ohm's law, where we can say that IB is equal to VR4 over R4, and we can use that to find the voltage drop. So we can say that's going to be 2.295 volts over, I think the voltage is the resistance is 1K, and of course since it's 1K, it's going to be the same for both of them. So 1 kilo ohms, which gives us 2.295 milliamps, sorry. Right? Now, of course, we know that whatever IB is, this is the same is equal to IC. This is also IC because they have the same resistance. Another way to find the current, if you know the total current and the resistances, is by using the current divider equation, where you can say that IB is equal to the opposite current. It's going to be not R4 but R5 over R4 plus R5 times the source, the current coming in, which is going to be IBC. And that gives us okay, that gives us 1/2 times 7.7 7.74 which gives us 3.887 milliamps. Okay, so the question is, why did we get this one here? Let me just look at it again. I think we may have a problem. All right, let's see what the issue is. So these currents need to add up to our total current. So IA plus IB plus IC need to add up to our total current. So again, you can see here we have 3.87, and if we have 3.87 plus 1.92 should add up to it should add up to 9.7. So the question is, why is this one we calculated with Ohm's law incorrect? Oh, I believe that the answer is incorrect here. Let's see. 3.66 minus 0.365 is actually not 2.9 but 3.29. So there should be a free hair. It should be a free hair. And so this would be a free hair as well. And so if we do this now, it should be 3.2. Right? So it's closer to the area. So again, we have some error. That's why it's 3.29 milliamps compared to this one. This one is correct too. We have some error with it as well. Okay. So again, this is solving this problem right here. So this document is going to be attached. You can click on the link in the description. So let's look at this last example for this series parallel circuits. Again, this method you just have to practice over and over again. Identifying the relationships, finding the equivalent, and then repeating the steps. So I simulated this circuit here with a voltage source of 24 volts. And notice the loads for the different resistors here. We have 400 ohms here, 1K, 1K, and 470. Now, of course, notice that these two are in series, and this one is in parallel here. So we can first, in solving this, of course, you see the total current that we got here from simulation. And we have the total current in IA here of 14.35 milliamps, a total current in this area here of 9.76 milliamps. Okay, notice also we have a voltage. Our voltage has dropped from 24 to 14.3, so we can find the difference in voltage here. So let's just find this. VR1 is going to be equal to this 24 minus 14.3. So 24 minus 14.353, that gives us 9.67647. So this is the voltage drop here across R1. So we will also find it by calculation, right? So if we know the voltage here, then we can find the current here. So the current here is going to be equal to, the voltage that's left is actually 14.35, and so if we can find the current here, is going to be the voltage over the resistance, so that gives us 14.35 milliamps. So this is correct. And then the current flowing here is going to be the total current minus the current flowing through this branch here. So again, if you add these two branches, it should add up to the total current here, and this is what we have as well. The voltage drop, the voltage here is 4.5 volts across this last resistor. So then we can find the voltage across R2. So VR2 is going to be equal to 14.353 minus 4.5891, and that gives us 9.7639 volts. So this is the voltage drop across this R3 as well. This is VR3, right? And of course, the voltage drop across this resistor is going to be 4.5. So let's solve this as we go. So the first thing we need to find the total resistance, right? So RT is going to be equal to, so if we look at the relationships between this, we can write a statement that essentially captures our total resistance. That statement says that R1 is going to be equal to, R1 is in series, so we say R1 plus, and then it is going to be in parallel with this guy here. R1 plus R2 is in parallel with what? It's going to be in parallel with the two of these, right? R34. Now, I'm just going to say R3 plus R4 because they're in series, right? So we know the total resistance is going to be a plus. So I can put it right here. So again, this is the total resistance we have. R34 is in parallel with R2, right? These two make one, and it's in parallel with R4, and then it's going to be in series with R1. So let's solve this quickly. Maybe we can solve it even as one, right? So you can see here we're going to have 400 plus 1K times these two to find R34 is going to be equal to R3 plus R4 is equal to 1K plus 470. So this time, so I'm gonna replace this with 1,470 over 1K times 1,470. Right, and that gives us total resistance of, okay, so this is product over sum. Right, the total resistance here is 473. Okay, when I add this to 400, it becomes 873.68. That's the total resistance of the circuit. Knowing that, we can find the total current of the circuit. IT is going to be equal to VS over RT, which gives us 24 over 873.68. It gives me 0.0274 amperes, which is the same as 27.47. Right, this is the same as 27.47 milliamps. All right, so we have our total current now. If you compare this to the current that we got here, this current is showing 24.11 milliamps. So let's see if we have any errors in our calculations. 1/400 in parallel with 1K plus 400. Let's double check it quickly. Okay, so I have an error in my calculation. Instead of being 8470, okay, let's see. All right, so this is incorrect. This should be 595.14, and this will give us a total resistance of 995.14 ohms. And so then the current is going to be slightly lower. All right, so this gives me a current of 0.024117, which is the same as 24.117 milliamps. All right, and again, this is the same. It's very similar to what we're getting in our simulation. So now that we have our total current, we can find the voltage drop across this R1 here using Ohm's law, and this is going to VR1 is going to be equal to R1 times I, which is going to be equal to 400 times 0.024117 amperes, which gives me 9.6468 volts, right? Which is the same thing that we found, right? We found the voltage drop here to be about 9.646, right? Then we continue. So since we know the voltage here, since we know the voltage drop here, we can find the voltage here, because the voltage, again, the voltage here is going to be these two loads, the voltage drop here and the voltage drop here will add up to 24. And so we can find VR2. VR2 is going to be equal to VS minus VR1, which is 24 minus 9.6468, which gives us, let's fix that. This gives us 14.3532 volts. Right, so knowing VR2 now, we can find the current going through this, because since we know the voltage across here and we know the resistance there, we can find the current. All right, so current is going to be equal to IA. It's going to be equal to VR2 over R2, which is Ohm's law. So we have 14.3532 over, I think, is it 1K? Okay, it's 1K, and that gives us 14.3532 milliamps. So if we know the current going in IA, then we can know the current in IB, because these two currents need to add up to the total current. So we can say that IB, this is Kirchhoff's current law, is equal to IT minus IA, which will give us 24.117 milliamps minus 14.3532 milliamps, which gives us 9.7638 milliamps, right? So this is the current in IB. And now, knowing the current, we can find the voltage across this resistor and that resistor. Again, the two voltages should add up to the voltage right here, right? So these two voltages should add up to VR3. Now we can simply use the voltage divider equation to find the voltages instead of using the current. So again, we can say VR3 is equal to R3, that's the voltage divider method, over R3 plus R4 times VR2. So the voltage drop is a fraction of VR2. So here we're going to have here, I believe it's 1K and 470, okay. So this is 1K over 1.47K times VR2 is equal to 14.3532 . And that gives me 9.764 volts. Now, if we know that this is the case, we can find VR4 is going to be equal to VR2 minus this VR3, which is 14.3532 minus 9.764, which gives us 4.589 volts. So this is the voltage that is across this last resistor. So again, the same method we're following. So you can see that our answers are very similar to the simulation, right? Same voltage for VR4, same voltage for VR2, for this voltage right here, this is VR2, same voltage for VR3 as well. Okay, so again, the steps that we discussed, you need to identify the relationships between the resistors, whether they're in series or parallel, and then you solve that equivalent resistance and you replace it with that resistor. And you keep doing so until you have all series resistors, all parallel resistors. So this is Prof. Skangrella signing off. Look out for the next one.